Okay. So, good morning. Welcome to the last day of build. Are you still excited? Woo! Pretty much so. Very good this early in the morning. So I'm Mads Torgersen. I am the PM for the C# programming language. That means I run the language design process, and I also maintain the language spec. So if you find bugs in that, it's my fault. For the past about 2.5 years, or 2.5 years ago, we kind of realized that if we wanted to move the needle in asynchronous programming, we needed to seriously evolve both the libraries and the language. And so back then, I started to pull together people from across the company to figure out what that would look like.
Yep. My name is Alex Turner, program manager for the VB C# compiler, so more on the compiler side than the language side. And for the past 18 months, I've been working pretty closely with the Windows team to figure out really what does it mean for VB and C# to be an awesome first-class citizen talking to the Windows runtime. And specifically, we've been spending a lot of time figuring out how the async model that Windows Runtime exposes can actually be projected really well into .NET, where we're already doing a lot of this awesome async stuff for this release.
So this is sort of the nuts and bolts talk about how you do asynchronous programming in C# and Visual Basic, in particular with a focus on how to do it with the Windows Runtime around. It should be no surprise to you by now that there's a big focus on asynchrony both in the Windows Runtime and in the C# and Visual Basic languages and in .NET in general. So why are we so interested in asynchronous programming? Well, asynchronous programming is a really good medicine for blocking threads, and we don't like blocking threads. Why don't we like blocking threads? Well, if you're in a client, in a UI thread, blocking the UI thread is bad for responsiveness, obviously. If you're on the server side, it's also bad to block threads because that means that thread cannot participate in producing throughput. And so you need more threads to do that, and ultimately threads can become a bottleneck and you hurt scalability. So blocking threads is bad, and asynchrony helps with that. That's really the focus. That's the reason why we're so interested in asynchrony. And that is indeed becoming the norm across many frameworks and languages, not just in Microsoft, but sort of across the world. But the abstractions we use for expressing asynchrony are also evolving. We're getting more modern abstractions that we can work with. And indeed, the asynchronous framework itself is evolving its model of asynchrony. Across many models, indeed, across Windows Runtime and the .NET framework, also JavaScript, there's sort of a general concept that we sometimes call futures, where you represent ongoing work and ongoing activity as an object that you can interact with, a first-class representation of ongoing work. We call those futures. And both the .NET framework going forward and the Windows Runtime are based on such abstractions. They're not precisely the same, but they're close enough that it's really smooth to interact between them. So that's what we're going to look at more in this talk. Here's an example of some synchronous and asynchronous code. I download data. That takes some time. You may have seen this slide before. And so what happens when I call download data on the thread that I'm on is that the thread blocks for that amount of time. And once I'm done, I can just go and process the data. If I'm asynchronous, here's an example of some asynchronous code written with a future-style abstraction. I call download data async. That's a future-based asynchronous method. It's immediately going to return to me a placeholder for the eventual result I'm going to get. So I can go on to other stuff, but I have to tell it. So through a callback here, I'm telling it what to do when the result is ready. I have to do callback-based programming. And of course, the advantage of that is that I only spend time on my thread when I'm kicking off the download, and then sometime later again when I'm processing the data. But in between, I'm free to do other stuff. If I'm on the UI thread, I'm free to handle UI events, update the screen, and so on as things go. I'm responsive. Right? Whereas on the synchronous thread here, all those events will get lost or happen sort of at the end. I'm sure you all know the feeling of having an unresponsive app that you've been trying to click on and move around, and all of a sudden all those things happen at the end. So that's sort of the core value prop. You can see that it gets even more interesting if you think about downloading things twice. Right? So I download synchronously. That means my thread is blocked, so I can't download the next thing until I'm done. And essentially, the time until I have the result is 2 times the time it takes to download. Whereas in the asynchronous case, I can kick off 2 downloads, and the time to last byte, so to speak, is only the time for the longest one to complete, which is, again, more efficient. Now, So clearly asynchronous programming is good, but it comes at a price. You can see it's more complicated. I have to sign up callbacks and stuff like that. And that is really the core problem that we want to address with the new language features in C# and Visual Basic. The essential value proposition of C# and Visual Basic Async is that they let you do asynchronous programming without expressing callbacks. Okay? So more generally, the philosophy is that doing asynchronous programming should be able to feel just like doing synchronous programming with bits and pieces dropped in. That's the goal. That's the sort of design philosophy of asynchrony in C# and Visual Basic. So in this talk, we're going to dive into a Metro-style app that we already wrote, so you don't have to see us debug through all our bugs in there, that is already asynchronous. And we're going to go and improve it and look at the various aspects. First, we're going to look at the language features themselves, and then later we're going to do some tricks that help us parallelize and coordinate our asynchronous activities.
All right. And so I have the app up here in Visual Studio. Take a look, just quickly run it so you can get a sense of what the app does. And this is a simple app we threw together from one of the templates. And really, it's about building photo mosaics. That's the gimmick for our app. And you may have seen photo mosaics before. It's this general idea of building up one larger image from a set of smaller tiles. And we have the app figure out which tiles go where so you can represent and approximate the original image. What we have on the left here are a set of Flickr tags. It's going to go out and request images based on a search to Flickr, pull back tile images, and then figure out where those tile images could be arranged to fit a user image. So I'll click here. You see I have a photo of me presenting a few years back at Tech Days Belgium. So this will be the photo that we target. And so now it downloads tile images from Flickr. You don't want to sit here and watch it download. We have them, some of them cached already. And then it did the query, though, pulled it back, figured out which images are there, looked them up, and then did calculation for about 10 seconds, figuring out which images go where, and sort of have a first-order approximation of my face back from that conference.
I think it's really beautiful. I really like the idea of an Alex made up of flowers. Don't you think it's beautiful?
Metro-style Alex, yeah.
It's Metro-style.
So this is the app, and this is what we're going to explore and figure out cool ways that we can make this app a little better. So if we take a look at the code, really the app we have here came pretty simply from one of the templates. Remember, there's all the different templates across all the languages, JavaScript, C#, VB, C++. The template we use here is the split application template. And it's a simple template. It's what you saw. On the left, it comes with a set of tiles. So those are scrollable. You tap on the tile you want. And then over on the right, you're going to have some sort of details. In our case, that's the mosaic generation process. Okay, so we got that XAML there, and inside our app, really that scrollable list on the left, that's the item list view. And so whenever the user changes the selection there, that's the event we care about most. That's where we're going to do our program logic here. So we take a quick look at what's going on. This stuff is really what we'd expect up here. We're getting the particular object the user clicked on, get back our mosaic model type, we can figure out what the tag is. And then we're going to go and do our different stages here of development, right? So we're going to choose the source image. This is the big image that the user is going to pick. For me, it was the photo of myself. And we're going to do that using a file open picker. This is the WinRT type. We hover over var to see exactly what type this is. It's windows.storage.pickers.fileOpenPicker. So it's in a Windows namespace. We know it comes from the Windows runtime. But I can use it just like a .NET type. And so I'll pull this in here. I bring this in. I set a few things, set up the file type filter. So we pull in images. And I can say I want to show them as thumbnails in that view. And so now I've pulled the image in, and the user is going to want to choose it. And so I want to say here, pick single file async. This is actually where we ask the user to choose the image. This shows that UI, that Win8 UI. And you notice this is where we're starting to do an async operation. The operation itself ends in async, so it's pretty obvious it's going to be async here.
Bit of a giveaway, yes.
Yeah. And we're awaiting it. And so this is where sort of the magic that we've seen, and you've probably seen earlier in the conference, actually happens here.
So what's the thing you're awaiting there? What's actually coming back from the pick single file async method?
Yeah, I mean, you can see, I'll hover over it, and when I do, you see that it's even giving me a further hint that what's going on here is something that I should be awaiting. It tells me that it's awaitable. And really the sense I get from that, when it tells me awaitable, that means it is one of these future objects. It means the thing I'm getting back is something that I can I can pause on to figure out later when it completes. And if I dig in to take a look at pick single file async, we see that what it's returning is a pick single file operation. And this is a particular WinRT class. If we dig in, we see again it's defined in that pickers namespace in Windows. But what it specifically implements is this iasync operation of storage file interface, iasync operation of T. And this is a generic Windows runtime interface that represents a future object. It really is the Windows runtime equivalent of task of T, if you've seen that on our side, on .NET. And so you have really the .NET task, and you have the Windows runtime iasync operation of T. They're both these types that represent futures. And so I come back here, and so now I have that. I know it's a future. I know I should be awaiting it, both because it says awaitable and it says async, and so I await it. And what I get back is that object I expect. I get the storage file. This is the result type. We saw it was async operation of storage file. That's what I get back.
Right. So here's where we should really look at what does this await really, really mean. I know you've seen it a ton of times. Maybe you already sort of fully understand it. Maybe not. So let's dig into what is really happening when you await. There's no callbacks in sight, but something asynchronous is happening here. And what is really happening is that we take the rest of this method, whatever is supposed to happen next, and we sign it up as a callback on that future object that we got back from the method. So we say, dear future object, when you're done, go and do this stuff. And that means we don't actually have anything left to do right now in the method. We're done. Whatever comes after happens later. So at the point of await, we actually return from this method, which is what gives us the responsiveness, right? Because we return out to something, whatever called the event or whatever, and we're quickly back out at the message pump. And it can do something else and be responsive until such time as the future finishes, comes back, schedules the rest of the method back on the UI thread, and eventually pumps it out and runs it. And when it runs it, the result that it produced comes back out of the await expression and can now be used in the rest of the method. Right. So that's really what happens under the hood.
And if we take a look at the rest of the method, what do I want to do? Well, I want to go on and do further things. In this case, I'm doing another await. It happens, right? So I take that original file, I call a method on it, open async. This is going to be another awaitable method. I see it's returning another awaitable object. And so I await it, and I get back, a stream, which is what I want. And then I can just continue on. I start doing more WinRT stuff. I'm making a bitmap image. You might recognize this if you've done XAML and WPF or Silverlight. This is how I'm creating XAML image sources that I can pass off to my UI, so I can display. Shows the image up there in the corner. And then so now I have the image, and I go on to say, all right, well, we got our source image. Let's get all the tile images. And so I do similar kind of stuff. I call one of my little helper methods to get a Flickr URI for the particular query, whatever the keyword was they tapped on. And now I'm calling another method here. I'm calling getAsync. And if we look, getAsync here is a .NET method. This is on the HTTP client. This is a new networking API we're introducing in .NET 4.5. And I'm calling this in order to get the result back, the XML result from calling that Flickr query to see what images I should be using. And again, just because I hover over this, I see it's awaitable. It's this task of T, in this case, HTTP response message. And so I'm able to await it, and when I do, I get what I expect. I get out the HTTP response message once that comes back. It could be immediately, it could be in a second, 10 seconds, but my method will resume when it's done. And
so task of T is really the .NET future type.
Right.
So now you've seen the future type, the type that represents a future from Windows Runtime and from .NET. But we can await both. Like the situations are extremely similar. You call a method that ends in async, you get something back that you can then immediately await. And what's interesting is that C# or VB don't really care what kind of thing you await. They just care that it has a certain shape that lets them await it. So there's a certain pattern that if your type follows that, a certain method that it needs to have, you can put it on with an extension method if it doesn't already have it. That if you have that method, it has the right shape, then your thing can be awaited. You can build your own awaitables if you want to, though that's pretty rarely needed. I haven't actually needed to do it yet. We essentially, in the languages, abstract over the different kinds of awaitables, and that's what allows us to integrate between these different worlds and also other worlds, like F#, for instance, has its own kinds of futures. We can await those as well.
Yep. And so just like before, I proceed on. I go do some more stuff. In this case, parse the XML that I got back. I pull out a tile list. I'm calling another method. In this case, I'm calling a helper method that we've written elsewhere. And this one, again, is a .NET method because we wrote it in .NET and C#, and it's returning a task of list of storage file. And so what I get back finally is that list of storage file. It's all the file images that we downloaded in order to display and to analyze. And so then finally, the last stuff we do, we just call another helper method here, another task returning method, create the mosaic. In this case, we're doing a bunch of CPU processing. This will take about 10 seconds, but we'll keep the UI free because we're awaiting it and keeping it free. And then we go on, same logic again to display it in the UI, and then we're done. So that's what our code is doing now.
Right, so there are a ton of awaits in this method. And if you think about it, they're really slicing up the method into little bits that get triggered onto the UI thread one by one as the result they're awaiting is happening. So it's pretty much the slicing up you would have to do manually if you didn't have these language features. Now, I noticed that a couple of the last methods you were awaiting there were helper methods that you've written yourself.
Right.
And so we're not just calling asynchronous methods from frameworks, we can build our own asynchronous method. Indeed, this is an asynchronous method that we wrote.
Right.
And we want to build our own result-yielding helper methods as well, ones that return tasks.
Yeah, and we can see, for example, if we look at the method that we were just in, we'd already added, when we started, to the event handler, this async keyword. That's what lets us write await inside the method and tells the compiler that we're going to be slicing the method in this way. And so we really want to be able to pull out our own methods, like the helpers you saw us call. And so we take a look at this method. It's working today, but it's getting a bit long. There's really all this logic here to choose the source image. And we may just want to pull this out and make a helper method out of it. And so let's see what that would look like. The one thing we notice first, if we just take a look, the only thing from here that we actually need to use is this original file. That's the one thing we use later to send off when we're making the mosaic. So we just need to make sure our method returns that back to us. So we have it later. So we're going to go here and select all of this code. This will be the code we extract out. And up here, I'll make our helper method. And so we know it's going to have awaits in it, so it's going to want to be asynchronous. And the event handler was void because we didn't care when it returned. It was just called by the message pump. But now, in this case, we do care when this method returns. We care enough to know when it completes. And we also care what the return value is. So we're going to use that future type in .NET task to let us do that. And so I'll say here task. And the thing we want to get back is a storage file. So I'll say task of storage file. We'll call this choose source image. We'll put the async suffix on so we know it's async. And the one thing I want to send in is the mosaic model, whatever the user happened to select. And so I paste our code in here. And then just the one extra thing we want to do is return that original file that we need back out in the first method.
So something interesting is happening here because you're returning a file, but the return type of the method is the task of a file or storage file.
Yep.
So the interesting thing here is we're not actually returning a task. When you make an asynchronous method that specifies it's returning a task, then the compiler will actually generate that task for you. Remember what happens when we execute an asynchronous method. We execute up until the first await, and then we actually return. Okay? We return at the await and sign the rest up for later. So at that point, the compiler is generating us a task that we can return to our caller, representing the eventual outcome of this method. So when we get to the return statement, it's not actually returning because we already did that long ago to our caller. What it's doing instead is going back to that task that we returned long ago and telling it, now you're complete. Here's your result. So that whoever's awaiting that task at that point will get that result out of the await and will move on with their work. Yeah. So in that sense, we're using task to wrap up the result and emulate the propagation of result values that you know from synchronous code.
Yeah, and the really interesting thing going on here is that you notice I'm awaiting these WinRT operations, pick single file and stream retrieval. These are WinRT operation classes. But even though I'm awaiting WinRT types, I'm able to return a task. And so whenever we're making methods, we're using task as our abstraction, but we can cleanly await .NET tasks, WinRT operations, any other awaitable things, and merge all those together into whatever task we're returning to represent our operation.
Right. I should say here that C# and VB do have a special relationship with tasks. Tasks are the only kinds of things you can return out of async methods. We don't let you return other kinds of futures. It's really easy to take the task or the func of task, if you want the whole method, and wrap it up in other kinds of futures. Mm-hmm. So thin wrappers can do it, but we don't actually support multiple different kinds of futures here.
Yep. All right. And there's one extra thing to do back here, obviously, is to call the thing that we created. So I'm going to say var original file equals await, choose source image, and pass in our model.
So we're passing along a result back through the await. It comes out of the await when the time comes. But another thing you can get out as an outcome of a synchronous method, at least, is an exception. So what happens if an exception occurs up in our method up here? That would be interesting to look at.
Well, so if we go back up and look, there's various places where exceptions could happen. One of them is going to be here. Imagine pick single file async, right? There could be something that goes wrong with this operation. One of those things that is good to know about a file open picker is it requires this file type filter property, right? It gives you back a collection. We're using collection initializers to add to it. But if you don't actually add any types to it, it's not going to know what to show. And so it'll be an error for us to actually call it. right? And so if this was a synchronous call and we called it, we'd expect an exception back when we finally call pick single file async. But in this case, we're calling an asynchronous method, and so it's giving us back this future object.
Right, but that's an interesting thing of futures. That's why futures are such a good modern abstraction, is they wrap not only successful outcomes, but also exceptional outcomes. So a future can also result in an exception and represent that, again, as a first-class object.
Yeah, and so in this case, there's going to be an error that comes out, and it's going to surface here at the await. The act of awaiting it, which normally gave us the result, is now going to actually be the place where that exception is thrown, right? And so we're going to have this exception surface from our method. Now, we could decide to catch it here, but actually one thing you often do with exceptions is let them bubble out to outer methods. And then you put a try-catch handler in that outer method, and let that be where you deal with the exception. And it's no different here with async methods. And so if I don't handle this here, which I'm not going to put a try-catch, the exception bubbles out. And now the task that we're producing is also going to end in this accepted state where an exception is produced. And so now, if we look down to where it's awaited, we're awaiting this down here. Instead of having a return value surface here, the exception is going to surface here. So just like with synchronous methods, you call them, we're getting this back. We're getting the exception back.
So you see how the exception propagation that we know from synchronous programming is emulated here again with this chain of wrap, throw,
right.
and things come out at the right place just as you'd expect.
And so therefore, what I can do is just what I expect with synchronous code. Take all of this. You saw me put it inside a try block. I'll say here, catch. In this case, we'll just catch all exceptions. And inside here, we're just going to do something simple. We'll say, update the status text and say, oops, an error occurred.
Okay, and we actually have an error, so I want to see some failure. Can you run it, please?
This is the good kind of failure in a demo.
Yes, the kind you learn from.
And so we click this, I click flower, and we don't even get the picker because the argument was invalid, and so we get an error occurred that shows up here. And we were able to catch this exception that bubbled all the way out.
And the other thing about this kind of error is that you forget sometimes to remove it from your demo. So while you do that, I will speculate. So what we've done so far is really just emulate synchronous behavior with await here. But we have this nice first-class object. We have the futures, the async operations from Windows Runtime, the tasks from .NET. And it's kind of a shame that as soon as we get one, we immediately await it. Like, there must be more we can do with these objects. Indeed, we sort of have a separation between kicking off the asynchronous operation and consuming the result. A separation that we don't have in synchronous code, but that we could have here if we weren't consuming the result directly.
Right.
So let's try to separate those two apart.
Yeah, and just to be clear, right, you see us doing stuff that's pretty convenient, like we're awaiting create mosaic and getting the result, awaiting this and getting the result. You know, often if you do want to use the result right away, if the very next line is going to be processing that result and doing something with it, then you're doing the right thing. You're awaiting it, you're using it, that's great, that's perfectly good. The one issue, though, is that you don't always use things right away, and you're perhaps leaving some performance on the table. So let's see what we can do here. If I say var original file, well, instead of awaiting it, let me get rid of the await. And we know this is going to return a task, so let me just say var original file task. And now we see this returns task of storage file, and now I'm just getting the raw task of storage file out on the other end. And so now I can just say here var original file equals await original file task. And so now I've separated this out into two lines. It's not very interesting. I just made an intermediate variable. But I'm able to do that because this task is a real object, a future object that I can hold on to. And so now that I've done this, though, if I look, the only place I'm actually using original file is all the way down here. When I calculate my mosaic, I send this off to say, here's the image file that you want to load and analyze. So I don't actually need to do this right away. I can take this and put it all the way down here, put it right before the call to create mosaic async. And now, if you look, I'm able to do all of this stuff in the meantime. I'm able to download my tile images and go out and do my request and fetch and parse my XML and do all of this while the UI is showing for requesting an image.
So while you're trying to decide which of all those nice images of you at other conferences to make a mosaic out of, we're actually going ahead and downloading a bunch of stuff. We're essentially doing stuff in parallel, even though there's no extra thread, there's no concurrency as such here, but we are having two different logical tasks going on at the same time. Whenever they need to do something on a thread, they put something on the UI thread in between their awaits. but they can interleave and they can take their own turns when they're ready for it. So we're essentially doing, you could say we're doing collaborative scheduling here. We have we have more than one thing going on at the same thread at the same time.
Yep.
Right? Which is pretty nifty, and without much ado, without much other than a little moving around of code here.
And it's simply this idea that you kick things off, right, when you know want to do them. I know I want to do this right away, show this UI, so I do it. And I just wait, I hold on to it, and I only await at the point that I actually need the value. And you just push that as late as you can, and you imagine a method that has all sorts of things when I know I need to do it, and later I use the value, and you just have this really complex interaction there, but you don't have to think about that. You just think about when you need things, when you want to await them, and you're just multiplexing the UI thread, being a good citizen there, and keeping it unblocked.
So I think this is really cool, and I want to do that with some Windows runtime methods as well.
So remember, we called two different Windows runtime APIs up here. We're calling pick single file async and open async. These are interesting things. Now, in this case, we happen to need the file right before you can open it, so we're not going to be able to do those things at the same time. But you could imagine the same kind of split. If I say here var original file, I'm going to say original file operation this time, right? Remember, we're just dealing with the raw operation for WinRT. So it says pick single file operation. When I go over here, we see, I'm getting the operation out, right? So I'm no longer awaiting it. And then down here, I would say original file equals await that operation. So, again, I just split this up into two pieces. And what I could put in the middle now, I could put some other work. So maybe I'll say here var, let's see, I'll just say await task.delay. Right? And task.delay, this is just a helper method that we have. We ship in the BCL now. And it gives you back a task that will complete after that many milliseconds. Right? So this is a task whose sole job is to trigger completion in 5 seconds.
That's a very useful thing to be doing.
A very useful thing. Well, we'll just use this sort of as a proxy for some very important work that's going on here.
It's kind of like when the boss says he's going to work on the budget and he goes in and just stares out of the window for a couple of hours.
Exactly, right. It comes back in 5 seconds, right? So there we go. We have our operation. We have something to do in the middle that we can think about. And so actually, let's take a look. I'm going to run this now with a breakpoint, and we'll see what happens when we step through the code that we just made. So I'll click flower again. And we'll step here, and you see I'm calling pick single file async. So this is the UI operation I'm calling into to show the UI. Now, it didn't show yet, right, because we asked to do a UI operation, but we're still in control of the UI thread, remember, until we await. So we would expect that now when we finally await, we return control, and it returns control, go back to the UI message pump, we want it to appear. So we hit F10, and
this will be good.
It comes up here, but we don't see it. The UI is responsive. You see I can hover, but we don't actually get the picker UI showing up yet.
Wow.
And so that's kind of strange. Why didn't it show up? I hit F10 again at await, and now we get the picker UI showing up when we're actually awaiting that operation we got back. And so that's not really doing what we'd expect. Why didn't it show up automatically? The whole point was to try to do this in parallel.
Well, that's kind of showing one of the important differences between the different kinds of futures we have. So Windows runtime futures and .NET futures are mostly alike, but an important difference between them is that when you get a task back from a .NET method, it's already started. So calling that method itself kicks off the operation, and a task just represents getting the result. When you get a future from Windows runtime, an async operation, you need to start it yourself. And the reason we haven't seen that being done yet is that await automatically starts it. Right. So that operation only gets started when you await it, not when you call the asynchronous method. Right. So we have to somehow bridge that difference. Yeah.
And so in this case, we've separated. We now care that it does start at the beginning, right? So we could make another line. If we take a look at the stuff that's defined on here, it has a start method, right? So we could start it, but it's not really fluent. It's going to return void. I'd have to make a separate line and think about that. Really, the better way, the fluent way to do this is to call this start as task method. This is an extension method that we ship that applies to async operation of T and lets us start it. It lets us kick it off, but not just kick it off, it also returns a task that we can use to track the completion of that WinRT operation. Right? And so if we look at start as task, we see it's returning a task of storage file, right? And so now I'm going to change the name of this, call it task, rename, and then see here, we're actually getting now a task of storage file. So we knew what the runtime type was. We have the strong typing because the generics are there in the Windows runtime. But we're getting back this storage file that we can think about when we finally await this, right? Awaiting it down here is still going to give us a storage file. But importantly, we now have a task. It's now started. And so when I run this, we'll go back in. We'll do the same thing again. I'm going to go tap on flower. And I start stepping through, and so we still have to wait for the UI thread to breathe, right? But now, while we're waiting 5 seconds, I can go here, I can click, I can use the UI, and then that stuff is happening in the background. And you see that after 5 seconds, my code continues. And then by awaiting it, we now get to do this, even though we were able to do that other work in the background.
OK. So let's go back to the slides and talk a little bit about what we've seen so far. This was essentially sort of the core of this was the entirety of the language feature that is being added to C# and Visual Basic, the await language feature here. So the async keyword, put it on a method to make it asynchronous, and to make it produce a task for you in case you're a task returning method. And the await keyword, use it to make the rest of your method a callback, then return and have it execute later with the result of the future you are awaiting. We saw some different kinds of futures. We sometimes call them awaitables because, hey, they can be awaited. And task and async operation, pretty much the same, except for that important fact that one is hot, we call it hot tasks, and another is cold, it must be started. So one's already running, one needs to be either manually started or started implicitly with await when you get it back. And there are a few other differences between these two types that we'll see later. But at the core, they can both be awaited. That's the 80% case. That's what you'll be doing most of the time. We also saw two different flavors of asynchronous methods. We saw task returning and void returning ones. And typically, you should always be writing task returning methods. When you return a task, you're giving your caller a chance to know when you're complete. If you return nothing, then they can't know when you're complete. Then you're completely fire and forget, and nobody can ever find out, at least not through those means, when you're completed. And so you really only want to do that when nobody cares if you're complete. Why would you ever do it, you say? I mean, shouldn't it always be safe to return a task? It's really just a convenience so that you can write event handler methods that follow the right delegate signatures that have void return types in them. OK? So we talked about the language feature some, and we sort of realized that the task type is a really central concept for asynchrony in C# and Visual Basic. And there are, in fact, a number of APIs that are really useful for producing and coordinating tasks. And we're going to look a little further at how they can play together with the asynchrony language features in the next part of the demo.
Sure. And so we'll go back to the demo. And we have our app now. It's working pretty well. But what else can we do? How can we improve the app further? Well, if we take a look back down at the original event handler, we see there's some places where we're doing this CPU-bound work, right? One of them here is parse photos from XML. This is a place where we're going to calculate what photos we want. We're going to take the XML back, munge it, come out with a photo list that we're going to hand off to the fetcher. The stuff we've seen, we see the app is pretty responsive as it is now. This is on our beefy developer machine. Maybe that's fine. But imagine that maybe the Flickr API is returning you more XML than you might expect for some particular query. Imagine you might be running on a slate, a tablet, where you just don't have as much power. It could be a smaller form factor, a slower CPU, and maybe this starts to take too much time to execute. If you saw Lesh's session, they sort of talked about the core philosophy in the Windows runtime for when they make operations async and when they care about responsiveness. And anything that could take more than 50 milliseconds is something that you need to take care of, in their case, to make it an async API. In our case, we think about that kind of threshold too. If we have an operation, some CPU work that's happening on the UI thread, and it's something that could take too long, we want to push it off. And we don't want to do that there. We want to put it to a background thread, right?
That's what I traditionally do. I take it and I move it off to a background thread, and then I'd suffer through the pain and agony of marshalling back and forth between my UI thread and the background thread. So how am I going to do that here?
Well, the thing we've seen before when we do all sorts of asynchrony, we do like sort of the network asynchrony, the file asynchrony. It's all about the await keyword and getting back this future object. And that's why I'm able to weave things in and do await within my code and have this nice flow. I really want to use await the same way. I want to use it on my CPU-bound work. And I can do the same thing using another helper method. We saw task.delay. Here's one, task.run. And the idea of task.run is it puts something off onto a background thread. In this case, I've called task.run, I made a little lambda, and I passed in the call to the synchronous method, right? And it's going to call that method and return the value. And we see that the synchronous method in question returns iList of photo info. And so that means that the run method that we're calling is going to return task of iList of photo info. And so it's giving me back a task that lets me track when this background thread doing the work actually finishes doing what we told it to do. And when it's done, it's going to give it back to me. This task will complete. I can await it. I can pull out the thing, and I get back that photo info.
And this actually shows another important thing about await. When you do an await, even though here we're actually running some work on a different thread, when the await completes, you come back in the same sort of context that you were in before you called the await. In this case, we were on the UI thread, so we come back on the UI thread.
Right.
Even though we were off doing work on a different thread.
Yeah.
So you can trust that. You come back in the same place that you were running before, so we can keep on doing UI work. It wouldn't be so fun if we came back on a random thread pool thread here, and all of a sudden we couldn't update the UI anymore.
Those are the times when you imagine today when you're using XAML things, you have to do dispatcher.invoke and figure out how you go back and forth between the different threads. And that's really what we want to avoid. We want to save you from that when you're using async here. And so you imagine this is a simple thing that I'm calling, but you could even be doing something a bit more complex, right? Like maybe instead of a single statement here, I have a block. And then I'm going to go put this here. I'll say, all right, well, maybe I'm returning this, right? So I've turned this expression lambda into a statement lambda. And I could be doing other stuff in here, and not just other synchronous things. Maybe I have something else I want to do. Maybe the boss actually wants to do his analysis here, right? And so I'm kicking off this other work here. And now I want to not just do synchronous stuff, I want to await it, even though I'm on a background thread. You think of all the async APIs that are going to be there in the Windows runtime and moving forward in the .NET framework, in the BCL. And all of these things are things you might want to do from any different thread. And so now I want to use await. Now remember, to use await, I have to mark things async. Now my method is marked async here, but remember, this lambda is generating its own little body that's going to be emitted off. So I have to make this into an async lambda. And so I just mark it async there right before the lambda. And now I have an async lambda.
And now actually, the lambda being its own asynchronous method, it's running in its own context. It's running on the thread pool. So the await inside of there will put the lambda back on the thread pool once that one is complete.
Right. And it's not about going back to the exact thread you started from, but just the same kind of context, right? We could be on one thread pool thread, await, come back, that one's busy, we go to a different thread pool thread. It's just whatever synchronization context we're in, the one for the core dispatcher inside the XAML engine for Win8 or for Metro-style apps, and then we go over back here, we're talking about just a normal .NET thread pool sync context. We're able to use whatever context we happen to be in to go back logically to the place where we left, so you can do the same operations.
OK, let's back out of the boss's 5 seconds of important work there. So now we saw another way of creating tasks. So they can come out of asynchronous methods, or you can create them by putting work on a background thread and getting a task for that. And we're really abstracting over the kind of ongoing operation that the task represents. So in a sense, task.run helps us unify concurrency on the one hand and asynchrony on the other. It makes it the same thing. It's really useful. You don't have, as a consumer of that task, you don't have to know, is it doing CPU-bound work, is it doing network-bound work, or whatever. It's all the same. Now, with all those different kinds of tasks in hand, it's interesting to see some more ways that you can coordinate those tasks with each other. Maybe many of you went to Anders's talk yesterday, and you saw him have a whole collection of tasks that he got from kicking off a bunch of downloads simultaneously. And if you have all these downloads and you want to wait for them all, it's kind of tedious to go through and await them one by one. And there's a helper method for that called task.whenAll. It just takes a collection of tasks and returns you another task that will complete when the last of those is complete. That's why it's called whenAll. Okay? So you can await that, and then you'll know that they're all complete, and you'll actually even get an array of the results of all those tasks if you do. We're not going to show that again here, but we're going to show a cousin of it.
Yep. And so what I'm going to show is task.whenAny. Right? And you might imagine what it does. Task.whenAll waits for all the tasks to complete. Task.whenAny is going to finish and give us back control when one of the tasks that we provided it is done. And there's all different cool, clever things you can do with task.whenAny as a building block to build up more interesting flows. One of the ones we're going to do right now is this idea of a soft timeout. If we go down here and we look back to create mosaic async, create mosaic async is something that could take 10 seconds, 12 seconds, right? And the user can move around in the app. The app is responsive, but they may wonder whether the stuff that they kicked off is actually processing. Hey, is it actually still going? And so let's give them an indication. If 5 seconds elapse during this processing, let's show a message to say, hey, we're still going. Don't worry, things are still calculating. And so I'm going to do the same kind of split here that you've seen. I'll say var mosaic task. I'll get rid of the await. And then down here, I'll say var mosaic equals await mosaic task. All right, so we've split this up into pieces. We now have the ability to interact with a mosaic task individually. Now, let's actually go here and just make another task then. I mean, we want this kind of timeout, and so one good way to make a timeout is using this task.delay thing you've seen us use.
So is this the boss staring out the window again?
No, actually, this time we actually do want a delay. So this is using it as a real 5-second delay. And this is going to be our timeout. This is how we're going to know whether we want to show this message. And now we really want to kick off both of these tasks. I mean, we've already done it, right? Because they're hot tasks, they're going. But we want to know which one completes first. Is it the mosaic task, in which case we're good, don't have to show anything? Or is it that delay task, in which case, hey, the mosaic's still calculating, 5 seconds elapsed, let's show it. So I'm going to figure that out by using this whenAny method. I call task.whenAny, and you see it wants some tasks, a params array of tasks here. So I'm going to say, all right, mosaic task. I'm going to say delay task. And I'm going to say var first task equals that. And I'm able to do that because of what whenAny actually represents. You see here that it returns a task of task. And this is
that's crazy.
It's kind of an interesting type, but it makes sense when you think about it. The outer task is just telling me when does this complete? When does whenAny complete? And the semantics of whenAny are it completes when at least one of the tasks completes, when the first one's done. But it's also returning a task. Its return type logically is task. And what it's going to give back to me is that first task, the one that actually finished first, be it mosaic task or delay task. So I'm going to know which one actually finishes. And so now I'm benefiting from the fact that these future objects are real, honest to God objects. These are real things. I can say here, first task, test if it's equal to delay task. I held on to delay task. I can do equality tests. And then I say, all right, well, if it equals delay task, then let's go ahead and say, all right, status, or let's see here, model.status text equals, we'll just say still calculating. All right.
Nice, let's see it.
Run this now. I'm going to go in. I'm going to tap on flower here. Pick our image. So we still have a little 3-second delay up there. Downloading tile images. And so now we're getting back. We're calculating the mosaic. This is crunching the numbers, figuring out which tiles go where. And after 5 seconds, oops, I guess I came too soon. Let's see. Indeed.
Yes.
Thank you. Yes. I need to await task.whenAny. And
otherwise you get the task of task back instead of the task, don't you?
Try it one more time here. Download the images, we're calculating the mosaic, and now we should find out which of those two actually comes back. We see it still says still calculating, and meanwhile the other task was already processing, and so now we get back our mosaic again.
So a couple of interesting things to note here. There's a good chance that when you get to await the mosaic task, that task is already complete. If the computation happened faster than 5 seconds, then the whenAny would actually have fired only when the computation was done. So here we would be awaiting an already completed task. And that's just fine. You can do that with tasks. They're very resilient to this kind of thing. Awaiting it may mean, okay, wait some time, get off the thread, come back later. But if the thing is already complete, that's fine too. You get the result or the outcome, the exception maybe if there's one of those. You just get that immediately. Indeed, you can do it multiple times. Yeah. You can await a task as many times as you want, and every time you get the outcome of it. Either you have to wait for it a little bit or not.
Right.
But you can always do it. So that's the standard way of getting the outcome out of a task.
All right. Now, one interesting thing as it relates to that, though, is we've been talking about task here. So you might imagine what happens here for the equivalent for a given winRT operation. And we come back here. We'll get rid of our boss work here. You come back here, and you see that we had been calling before for a different reason start as task on that original file operation, the winRT operation we did. And so if we wanted to pass this to task.whenAny, if we wanted to await it multiple times, we'd be able to do so. If we were just dealing with the raw winRT operation, though, we would only be able to await it once. And this is important to know because when you await a winRT operation, you are implicitly starting it. You're sort of converting it from cold to hot at that moment. And so you're only allowed to await it once because you have to sign up for the completion, do the start. You can't do that again later. So if you think you're going to need to await it multiple times, if you think you're going to want to do more complex operations on it, like you do on tasks, your best bet is just to go back and call start as task so that you have the ability to use it as a real task. One other interesting thing here is, we were going to call whenAny down below. Let's say we had some reason to call whenAny up here. if we were going to pass that winRT operation into winAny, we wouldn't be able to directly, right? Because what you saw was it wanted a params array of tasks, right? And so it's another case where if you need to treat it, you want to pass it to a combinator, winAny, and you have a winRT operation, just go call start as task, get yourself a task that wraps it, that represents the result, the return value, exceptions, and all that, and then use that as your task. And then you'll be able to do all the stuff you know how to do and that you're able to do otherwise with tasks.
So there's really a pattern emerging here where Windows runtime futures are very useful and you can await them directly. Task is really has a very rich set of helper methods and we call them sometimes combinators around it that lets you really coordinate them in very fancy ways. So whenever you don't have that facility available to you on the Windows runtime operations, just convert them to tasks and you're good to go. They easily become full-fledged members of the .NET asynchronous world, just with start as task. Start as task is really your friend. Whenever it doesn't work directly, start as task.
There you go.
Okay, so let's go back to the slides and talk briefly about what we've just seen. So the really sort of central message here is task is very versatile. It lets you coordinate and create activities in multiple different kinds of ways, so explore that and use that. A number of examples of that here, so some categories, if you will, some of the most common helper methods with tasks. Some of them let you yield control for a period of time. This task.delay that we've seen multiple times just creates you a task that will complete in 5 seconds. And it starts ticking the moment you call task.delay, and then whenever you choose to await it, if the 5 seconds aren't done elapsing, if the clock is still ticking, well, you wait until it has. There's a sort of little brother of that called task.yield that just lets you get off the thread and come back as soon as possible. So it lets you take a breather, for instance, on the UI thread saying, I want it to pump. In order to be responsive, maybe in a tight loop or whatever, I just await a task.yield in here, and every time around, I'm letting other things do stuff. For more heavy lifting, for if you're really doing a bunch of stuff that shouldn't happen on the UI thread, just task.run it, get a task back from that, and await that on the UI thread. And you have all your marshalling back and forth taken implicitly care of by await, just like it does with all other kinds of tasks, and really unifying those concepts. And finally, a couple of methods for parallel composition. It was easy enough, without any helper methods, to kick off multiple tasks and have them happen at the same time. The interesting thing is coordinating between them, and so waiting for the last to complete or the first to complete are some of the easy building blocks for maybe building more complex structures of flow of things. Some things happening parallel, then some things happen in sequence after that, and you can combine and mix and match in different ways using just these building blocks here. Yeah. So that's all about tasks as sort of atomic units in a way, and now we're going to sort of, towards the end of the talk here, as the last part of the demo, we're going to talk about situations where, asynchronous operations are asynchronous for a reason, right? There's typically long-running operations. And the thing about long-running operations is that you have time to change your mind about them, like, oh, I didn't want to do it after all, or things like that, right? So in general, you want to be able to communicate to a long-running operation and say, I regret that I asked you to start, or maybe the user pressed cancel or whatever. Could you please just pull up as soon as it's convenient for you? So cancellation, right? With long-running operations, you want to do cancellation. And the .NET framework has its own abstraction for doing cancellation. It really has a separate, again, it's kind of like with tasks, it has a first-class object for representing ongoing activity. It also has a first-class concept of cancellation. It really has a kind of object that represents cancellation, and we're going to use that.
And so if we take a look, we're back in the demo, and I can look at the methods that I'm calling, the ones I might expect that I want to cancel. And these are the ones that are sort of the longest running things that I do. And you remember there's that whole sort of 10, 12-second thing that occurs at the end where we actually generate the mosaic. And this is a helper method we'd written, and you can see that this task returning helper method, we actually have a third parameter that we hadn't been using. This is an optional parameter we had added. And this accepts a cancellation token, the type Maz was talking about. And yeah, it really is that first-class type that represents cancellation, just like we have the first-class types that represent futures in .NET and Windows Runtime. We have this ability to pass this in. And it's going to want this cancellation token to indicate, hey, hold on to it. We'll tell you, as the UI layer who's controlling the orchestration of these different operations, we'll tell you when we want cancellation to occur.
And so really by taking cancellation token as a parameter, you're signaling that you are willing to listen to it, to observe it, and observe any cancellations that get signaled through it. Right? So you offer up cancellation by taking a cancellation token as a parameter.
Yeah.
That's part of the standard pattern of asynchronous methods on .NET. Your task returning, your name ends in async, and you potentially, if you are cancelable, you offer up the ability to pass in a cancellation token.
And so we're going to want to pass that cancellation token to as many methods as we can. But first we need to get one. And the way that you get a hold of a cancellation token in .NET is another related type called cancellation token source. Makes sense as a name. And I'm going to make one here. I'm going to make it at class level. We'll see why I'm doing that in a second. And so I have a CTS variable. It's going to hold my source. When I actually kick off the operation, this is the selection change, I know I'm doing something that is potentially cancelable, that the user might want to cancel. And so that's when I'm going to initialize my new source. And so I have these two types now. There's cancellation token and there's cancellation token source. And if I think about the relation between these two types and why there's two separate types, well, cancellation token you can think of as sort of the light bulb that'll light up, and it indicates to anyone who's looking that cancellation has been requested. Right? So I'm going to hand this off to a bunch of different APIs. Some of them are going to hand it off to the APIs that they call. Remember, I'm calling a lot of my own helper methods. And so there's this whole tree of execution that's getting past a cancellation token. A single one is a parameter and spreading it out. And so all these people have a hold of that light bulb to know when cancellation should happen. And so on our end, we hold on to the cancellation token source. As the UI, we keep track of this object. And you can think of that as sort of the big red button. Right? And so we are in charge of hitting that to indicate we want cancellation. We want whatever is going on, whichever operation it happens to be, to throw in a cancellation exception, abort the process, bubble back out, and then we can catch it and do whatever we need to do. And so we have this ability to cancel anything that happens to be running, no matter what it is. We don't need to track what is the current operation so I know exactly what thing I need to cancel. It just cancels anything going at the moment.
Let's cancel something.
So we come down here. We'll go back to the one we just saw, create mosaic async. I have my CTS now, and the way I get the token from it is they say cts.token, and it returns us this object, right? And so I can cancel, create mosaic async. I can go up here and think, all right, well, fetching the images from the server, if we didn't happen to have them cached, that could take a while, right? So I'll pass a token there, right? And one other thing we might want to cancel is this choosing the source image. Right? Because there's file operations in there. There's opening the thing from disk. And so we probably want to go make even our own helper method that we just wrote cancelable also. So if I come up here to the method and I look, what do we want to do to make it cancelable? We're going to follow the same pattern we saw on the helper methods. And so I'm going to add a cancellation token parameter. I'm going to call it cancel. And just like we saw before, I'm also going to make it optional. It's important to know that you can just say optional here. I'll make the default cancellation token the one that I actually get back if nobody passes this in. Cancellation token's a struct, and so this is OK. The default cancellation token just happens to be one that will never trigger cancellation. So I can treat it the same way as a real object that I get. So I'll come in here. And now I might want to cancel this operation. This is the pick single file. But as it turns out, the user is going to be looking at a full screen UI. They're not going to be in a position to signal cancellation. So this doesn't actually have to be something that we make cancelable. But down here, this is, right? This is opening a file. Remember, this is a WinRT file API. And the reason we're using the WinRT file API is we could open any kind of file, right? Imagine in the picker, the user may have chosen something from one of those other apps, an app that offered something into the picker. It could have been Facebook app that's offering a photo from Facebook. Or it could have been something that's offering images from Flickr that the user manually browses to, right? And they're choosing that source image. And so we don't know. It could come over a network. It could take a few seconds to get back and actually download. We need to be resilient to that. And while it's coming in, we need to be able to cancel it if that's the current operation.
Sounds like we should pass it a cancellation token.
All right, so we go to do it, but we look and there's no cancellation token parameter. And so this is the other sort of the last thing to figure out the difference between WinRT operations and the .NET operations. We saw when you're making task returning APIs in .NET, you want to accept that cancellation token as a parameter. Right? That's the pattern. That's the sort of task pattern that we have moving forward for doing stuff that can be cancelable. You accept that token. But WinRT has its own notion of cancellation. And just like we called the start method, or we could have, to start it, you see on that object there is a cancel method. Right? And so the object, actually, if you look at WinRT operations, they have a native understanding and concept of cancellation. You can just cancel them directly. Right? And so it's fine. It's a different model. But we want to bridge between that. We don't want to have to think about, hey, if this is the current operation, go call the cancel method. And so if you remember before, start as task saved us from having to call start manually and think about that. It turns out, ironically, start as task actually is there to help us think about cancellation. So I'm going to go here. I'm going to call .start as task. And if I just did this normally, I'd get the same behavior, right? Because I'm awaiting start as task directly. But if I take a look at start as task, I see there's actually a second overload. And the second overload of start as task takes a cancellation token. And this is where cancellation token can start to participate in my use of WinRT objects, right? So now I have my cancel parameter. I'll pass it here to my start as task method. And now this bridge is in place. I have the ability to say, all right, I'm starting it. I'm getting a task back. And the implementation of start as task, it's going to register. It's going to say, I get back my CTS, or my cancellation token. I figure out, hey, when it actually triggers, register for a callback there, what it'll do behind the scenes, and then call that cancel method for me. So I don't have to think about the WinRT operation and knowing when to call cancel. It's as fluent as it was for me to do just with my .NET types.
So what I said before really still holds true. If it all aligns, fine. If it doesn't align, call start as task. It's probably your friend.
And so now that we have all this in place, I'm going to go here. We come back up. Now, if we actually think about what's going on here, remember, cancellation token has been bubbling all the way down to the lower level. What happens when cancellation occurs? Let's say that we actually trigger it and this is running. Well, the way we figure that out at the outer levels is a cancellation exception is triggered, right? And so we're going to have an exception that surfaces here. It's going to come out of the WinRT cancellation thing. We actually told it to cancel, and that operation is going to come back and cancel. And it's going to throw an exception, right? So when we await it, we're going to get this exception back out from the canceled state. Now, we saw exceptions flowing before. They're going to flow back out to the outer thing. We were catching the exception that bubbled from here originally. And so it's really just tracked exactly the same way. We come back down to our catch block, and we can now detect when cancellation has occurred. I'm going to say here catch. And rather than just general exception, I'm going to specifically catch operation canceled exception. That's the task return, or the task method that's, or exception type that's generated when you cancel something that's ongoing. And in here, rather than update the status text, I'm actually just going to say, well, let's take that whole list view on the left and clear the selection. And so now there'll be no selection, and it'll clear the view on the right.
But that's a really powerful paradigm. You take your cancellation tokens, you just spread them out into the world. Whatever is going on gets it, and whoever gets signaled cancellation throws an exception all the way back up, and somewhere at the top triggers whatever action needs to happen when a cancellation occurred. So there's this very nice spread out, come back up communication going on very simply just by passing out these cancellation tokens.
Yep. And so really at this point, the only thing we have left to do is actually trigger the cancellation. And so for the purpose of the demo, we'll just use the back button you saw in the corner. And when the user presses that back button, we'll use it to clear out whatever's going on at the time.
I'm sure that's not very metro.
Yeah, but it'll work for our purposes.
Maybe you could turn off the camera so the metro police don't catch wind of this.
So we'll say here, if the CTS object, the source is not null, which means we have something interesting going on that's worth canceling, go ahead and cancel it. And so now we got this going. We're going to run our app here. We'll see. And so now when we get back in, I'm actually going to choose a different set of images, right? It's one where we don't have it cached so that we have an opportunity to go cancel it. And you see now it's downloading tile images. My app is responsive, and I can hit the back button. And we're able to cancel the operation and clear things out from the right.
Right. So that's pretty much it for what we want to show in the demos.
Yep.
Let's go back and round things up. There's one more thing you may have been thinking about that's akin to cancellation. Another way you want to communicate with an ongoing operation itself, which is progress. So some operations report progress, and it's a similar kind of deal where you have a progress reporter kind of object, you pass it in, and it can get spread around and progress combined and so on. You can describe that logic yourself. Now, both cancellation and progress, as we saw, have a different model in the Windows runtime. Indeed, the future itself handles both cancellation and progress. So to bridge between these two models, we do as we always do. We call start as task and have it help us out. So we can pass in our kinds of cancellation and progress and have them wired up to the Windows runtime kind. So that's really it. I think sort of the main message to take away from here, if you remember nothing else, is this deal about no more callbacks. Yep. It's the fact that all else equal, a good start with asynchronous programming is to just structure your program as if it was synchronous and just have these little awaits and asyncs all over the place, and you really don't get much more complexity in the code. And then if you get courageous or you have perf issues or whatever, you can start parallelizing and coordinating and doing all this stuff as sort of an added bonus because of the richness of the task type. And then again, use cancellation and things to deal with the fact that you have long-running operations here. But really, the core thing is just this. In C# and Visual Basic, you will never write another callback in your life. Isn't that beautiful? Yeah. So just as we close off here, most of the related talks have already happened. There's one I want to point your attention to, which is going on in the next time slot, I think over at the Marriott, which is Stephen Tope talking about the Zen of async. He's really going to dig a layer deeper, at least one layer deeper than we have here, and look at what is actually going on under the hood. How is the callback signed up, and all those kinds of things, and what are the perf implications of that. So if you really want to dig deep, go and see his talk next at 10:30, I believe. That's pretty much it. Here is some further reading, some documentation about the new features in C# and Visual Basic, and an async homepage where you can go and read white papers and so on. And please give us your feedback, give us your questions, and let us know how we're doing, what we should change with async, so we still have time to fix it before we finally release this stuff. Thank you very much.
Thanks.